In this video, we're going to be discussing section 6.4 in the textbook, which is called Method of Sections, and this is applied for trusses. So far what we've looked at is method of joints for truss analysis. Now, the reason why you would use method of joints is to find all member forces in a truss. So let's make a note of that. We're going to say method of joints is best used to compute all member forces in a truss, okay? Now, method of sections, on the other hand, is much better to use when you want to calculate specific forces in specific members. So we'll make a note of that. We're going to say method of sections is best used when only certain member forces are required. Now, in both of these methods, you're going to get the exact same answer no matter what. These are both what we call equilibrium methods, so they will yield identical results. It's just which method is better to use under which circumstance. And again, method of joints is best if the problem asks you to compute all of the member forces in a truss, but method of sections is better when you only want to calculate member forces in certain specific members. So we'll make a note here. We're going to say both methods give identical results. And another thing I'm going to mention is for some problems, you may find that you may need to use a combination of the methods. So you can actually use the methods working together. Now, we're going to see an example of that later on in a later video, but just for now, I'm going to state that both methods can be used together in a particular problem. So, but again, you're only going to do that if you have a specific, unique problem that's asking for a member force, and you may find that based on the geometry of that truss, it's a good idea to use these two methods working together. So let's talk about method of sections. How does it work? Well, this is what we do. We, quote, cut a section through the members that we want the forces. So when we say cut, notice I put that in quotes. What I mean is we pass this kind of non-realistic imaginary section, we pass it through the specific members that we want the forces. And remember, I already said it a few times, we use method of sections when a problem asks for member forces that are in specific members, not all of the members, but just some of the members. So we cut this section through the members that we're interested in. Now, I do want to emphasize, we say through the members, depending on the geometry of the truss. I'm going to put a little side note here. I'm going to say we could say or through the members near the ones we want. And we'll see an example of that little side note that I just wrote in red in an example later on, okay? So we make this cut section through the members that we are interested in the forces, all right? And then what we do is we analyze a free body diagram of the portion of the cut truss on either side of the cut. So notice I underlined the word either here. What I mean by that is when we make this cut section through the truss, we're going to break this truss up essentially into two parts, right? Two sections, quote unquote, all right? and we analyze the free body diagram of one of those sections. Okay, that's why I underline the word either here. It could be, we could analyze either section of the truss. We don't have to analyze both, okay? So I'll make a little side note here. We're going to say no need to analyze both sections. ... Just one. All right. And the reason why is the whole truss in and of itself is in static equilibrium, or it should be. So that means when you pass a section through this truss and you separate it into two parts, each of those individual parts should also be in static equilibrium in and of themselves. So that means you can look at either one of them. You can analyze at either one of them. Whichever, I would say pick the section that has the least going on, I guess, has like the least number of forces and the least number of geometric irregularities to make your life a little simpler when you're doing this analysis, okay? So we'll make a note here. We're going to say analyze the section that is, I'm going to say, quote, easier to deal with. Okay. All right. Now, the next part, when you draw a free body diagram of whichever side you choose to analyze, you want to assume the member forces are acting in tension. Okay. So we're going to say the unknown member forces are the ones that the, quote, cut passed through, and we want to assume these are in tension. And so very similar to what we saw with method of joints, when you assume a member force is in tension, you point it away from either the joint or the free body diagram or whatever. In method of joints, we pointed those unknown forces away from the joint or away from the free body diagram we were drawing. So the same idea is true for method of sections. When we assume that these forces are in tension, we point the unknown forces away from the free body diagram, okay? And then again, we analyze one of these two free body diagrams that has been sectioned off. So we apply 2D rigid body equilibrium equations to analyze one of the free body diagrams. And remember, you could maybe pause the video and remind yourself, what are those 2D rigid body equilibrium equations? Pause the video because if you want to figure it out yourself, because I'm about to tell you. So there's three of them, right? There's some of the forces in the x direction equals 0, some of the forces in the y direction equals 0, and some of the moments about some point, I'm going to call it point O, equals 0. So we apply these three rigid body equilibrium equations for a 2D system to one of those truss segments, okay? Now, just like before, just like with method of joints, we may or may not need to solve for external support reactions at the beginning of the process. Okay, so depending on the truss geometry, you may have a truss geometry or a situation where you've got to solve for some externals before you do method of sections. Or you could have a truss that has geometry that you don't have to solve for external support reactions before you start the process. So that's going to depend on that specific problem, and we'll see a couple of different video examples illustrating these.